Alfred has a very rich background, and we're actually switching gears a little bit here and going more to the packaging, interconnect, and assembly area. So he's going to talk about solving Moore's Law packaging challenges, how we need to change and morph in order to meet the new needs, and how copper in particular is key to that change in the industry. Alfred is founder and CTO of Kuprion, if I said that right, a materials company incorporated in Delaware. He has a rich background. He got a PhD in chem in Germany, and then he went to a postdoc at UCLA where he spent quite a bit of time. He went from there to Boeing and then to the European Space Agency. Love to probe that a little more. And prior to his present assignment, he was with Lockheed Martin as a fellow in the Advanced Technology Group for many years. He was responsible for development of nanostructure functional materials, and I'm sure that led directly to what he is talking about today. So, Alfred, please proceed.
Yes, thank you, Dave, for this kind introduction. That is correct. So in the following, I want to introduce you to our new materials, very versatile material system based on nano copper, which I developed at Lockheed Martin, or where it started. And in order to put this into perspective, as you said, with Moore's Law and the industry as a whole, I'm going to take a step back and look at what happened in the last few years. And when we look at it, we have seen a radical paradigm shift in the electronics industry as a whole, triggered by the IC scaling, plateauing, hitting a roadblock really, and with that also performance of electronics in general. And of course, it's all about Moore's Law, which was always an economic law, that was officially put to rest at that point because there were no more advancements to be made. And with that, of course, the corresponding ITRS terminated in 2016. So up to that point, the entire industry, when you look at it, was aligned to IC scaling and focused on the next smaller node. And that was really the growth engine of the whole industry. And that is no longer. So how do we keep growing and improving electronics? And already Moore identified that next thing, if you want, and that's packaging, as the two gentlemen before me already showcased a little bit in many sense. And that's really the next area to tackle. And this was recognized industry-wide, really driving what is happening in the materials, on the material side, because packaging is a very complex field where many different materials are being used, and they have very different properties, but they're put together in very small packages, like system of package, system on chip, and things like that, which is reflected in what replaced the ITRS, which is the new HIR, or heterogeneous integration roadmap, focusing on exactly that. And here just I'm showing a few drivers in that area. These are data centers, especially many things around electric vehicles, autonomous vehicles, and 5G communication that's moving further on. And when you look at that, there are at the core a couple of key challenges that need to be solved. And they are that when you integrate things, you have the issue of getting the heat out. That is really the key in packaging. And thermal expansion when you put lots of different things very, very closely together. That is really the gist of the thing in packaging, and this needs to be solved. And our material can do that in many different ways. So when you look at that, when you have your electronics, you have your devices, which are either silicon or silicon carbide or gallium nitride or things like that. They have very low thermal expansion. The more powerful these devices get, the closer you want them to be on your heat dissipating devices, which are always either aluminum or copper. They have very high thermal expansion. So how do you match that, especially when chips are getting bigger and they're getting thinner, so they're becoming, in essence, more fragile. And we're able to do that. So we're presenting our material as a solution, really a material system that is able to solve a whole host of challenges, starting with simple die bonding, to have a better thermal interface material, to have better electrical contacts when you compare it to solder, and can do many other things. Here's just a little image impression of the material. On the left is the paste in a syringe that you can sinter, you can dispense, and you can even do injection molding and make large heat sinks, heat spreaders, plugs, and things like that. So this is in the following. I will showcase the capability of the material with some very specific applications. One is LEDs, obviously die attach. It's a wonderful material. You can see here, you can dispense it easily from a syringe. You can spread it out. It's kind of like lotion. It's really thin and has this beautiful copper sheen when you do that. So very, very beautiful material. When you dig deeper, looking at the nanostructure, it is a nanomaterial. We have nano copper in there that's at the core, and it's heavily agglomerated. So it already comes from the beginning in this paste form. And when you fuse that, it all fuses together at a relative low temperature, about 80% below its actual melting point, to more or less solid copper. And all the additives and surfactants, they evaporate during that fusion, and you're only left really with pure copper. So a very good material to replace solder with much higher performance thermally and electrically than with solder. So here's some different flavors of what you can do with the material. It is very easily dispensable. You can make stacked systems. You can do actual full 3D integration, because you can do multiple layers. Once the material is fused, it reverts back to bulk copper. And that means you can heat it as many times as you want. So you can do 10 layers or 10 different reflow cycles. The previous ones, they don't do anything. They just sit there happily. If anything, they'll continue to sinter and become stronger and better. Here's an example of 1 millimeter LED dies on a chipset that was done with a production machine. Here are some 5x5 dies on an AMD silicon nitride system. We can do surface mount components here on the bottom left, through-hole connectors. Here's an example of a demo board with different everything from BGA to really small surface mount devices, and a 68-pin QFP. A particularly interesting thing is what I mentioned earlier. How do you match a silicon die, getting it close to your heat spreader or heat sink? How do you make that happen with the vastly different thermal expansion between the silicon and the copper? And you can't do anything thing with the silicon, that's a given. But we have been able to reduce the thermal expansion of our copper. And since we have it in this nice paste form, we can do very easy injection molding and make these heat spreaders or heat sinks. And now we have been able to make them with the same thermal expansion of the silicon. So there are no more thermal stresses. You can run this through, this is a 10 by 10 millimeter silicon. You can run this through thousands and thousands of thermal shock cycles. And because there's no stresses in this system, it stays put and stays very strong and continues to be working really well. So this is one very exciting implementation of our material and shows the versatility, all the different things you can do with it. So as kind of a top level view of the material, depending on the configuration, we have measured thermal conductivity as much as basically bulk copper. This is the latest data. Electrical conductivity is also very high. The reason for the spread is the way we have been measuring it so far, where we do screen printing. And because it's so thixotropic, you get a very rough trace line. And you have to assume some average thickness to calculate the conductivity, which is then, well, what do you apply when you have a very rough surface? So that's why I believe the electrical conductivity is very high, but these are the ranges we have measured with those printed lines. Shear strength is really good. It can exceed 100 megapascal depending on what size die you have. And it's compatible with all standard manufacturing as listed here. We have done all of them. It works great. Stencil printing, screen printing, dip transfer, you name it. Reflow ovens, we've done laser sintering, photo sintering. We did some fun stuff with resistive welding in air. I mentioned injection molding for large parts. So these don't require a nitrogen atmosphere. But when you do die bonding of LEDs, for example, or so, you need to do this under nitrogen until the copper is fused to bulk copper. You have to be careful.
Alfred, one quick question that popped up. Are there different specifications for different materials, or is this simply one material that you have?
It's really a suite of materials. So we make the raw material, the raw nano copper, as a raw paste, if you want, kind of like crude oil. And then you can formulate it in many different ways. And so we have a host of die bonding pastes. There are different requirements for like a 1x1 versus a 10x10 or a 15x15. Then we have other products I mentioned for these CTE adjusted heat sinks and thermal ground planes. That's a different formulation. And we do a lot more things. We do thermal vias that we can fill. We do this in through glass vias, for example, very small, different formulation, obviously. Again, the key there is to adjust the CTE so that it matches the glass and you don't get into issues with materials compatibility. Does that answer the question?
Yeah, it does very much. It generates the other question, though, is how do you get the CTE the same as silicon? That feels like difficult.
Yes, it is difficult. We actually do have a few different formulations. We have several proprietary fillers that we add to it that are low CTE and help adjust that. And depending on what you want to do, you chose the most appropriate one in terms of size, mostly. That you can either fill a small via in glass or a large via in a printed circuit board, or make an DBC aluminum nitride or things like that.
Thank you.
This is just a quick slide. I just love the colors. I had to show it. How to make the material. So we have a pilot production run already. This is a 300-liter reactor, and we already have a partner we have been working with for the last 2 years. They're going to bring an even bigger system online this month. And by the end of the year, we'll be at the ton scale manufacturing, and will grow from there very rapidly. So it's a beautiful material. The synthesis goes through a number of different fun stages because it's copper. You throw everything together, a precursor, your surfactants in a solvent, and then you reduce it. And in the end, you collect the material, and we use buckets or large cartridges to store material because it's pretty dense, so it's pretty heavy.
Is there a short shelf life?
Go back. Actually, no. The raw material you can literally store for years. We have 4 or 5 year old material. And in this state, it is really stable, and it gives you the beautiful opportunity to make to order. So we have, I think, currently over 200 kilos stockpiled. And so when somebody comes and says, I'd like a kilo of this formulation, we can basically turn this around in a couple of days. So that's very beautiful. The pastes, depending on the composition, the formulation, typically 6-7 month shelf life, and even the pot life is pretty good. So here, the material is RoHS compliant. There's a little further summary. After fusion, it's pure copper. Unless there are some CTE justice, but there are no, organic binders, which you see a lot with silver and other materials that much reduce its performance and its properties. So we purposefully chose not to do that, which is a bit of a challenge, but we were able to work that out. Sintering, it's pressureless sintering in the 180 to 235 range. Typically, we're doing 220 to 230. Depends on the specifics, and it's only a few minutes. It's like more or less a standard solder reflow profile. Once it's fused, it reverts to bulk copper, and then its melting point goes back to 1084 C. There's no migration, no whiskers or creep. It's actually very, very resistant to migration. We have done some interesting tests there. Another interesting feature is there's no liquid stage, so there's no wicking. So you can have contacts very, very close together, very fine pitch. And the CTE so far, we have explored the range from as low as 3 and 17 as the standard copper CTE. So here's actually an example that we just recently did. This is 15 by 15 millimeter silicon die on our CTE adjusted copper. You try that on normal copper, I doubt you'll even be able to stick it because it will pop off when you start cooling down. It comes out of the oven due to the high thermomechanical stresses that you have between the two. So on the thermal performance, we have done a lot of work with LEDs, and want to present here system level testing that was done by an LED company that we have been working together. So the thermal and the performance of the LED was done on the system level with this setup. And the results were really astounding. We compared it with the standard gold tin solder, the Eutectic 8020. Same system, same thickness, and we saw a 20 to 25% improvement in thermal resistance, which is plotted here. So you have the gold tin here in blue and the copper in a more yellow color. And it got better and better with higher power ratings. So this is really very, very amazing. It shows how much better the material is because you got bulk copper with much higher thermal conductivity than the gold tin solder. So very nice results. So further, when you compare it to the other materials that are out there, so we plotted here published data from SAC 305, sintered silver, our gold tin we tested, and our copper. So we're thinner bond line, which is really important for the heat transfer, and just much better performance. Here's another comparison, high lead solder, high thermal sintering paste, gold tin solder, and our material. So then optical measurements, anybody who knows a little bit more about LEDs, the performance is all about how cool you can run the LED. The cooler you can run it, the more efficient it is, the longer the life it is, and the higher your light output is here. And this was done in collaboration with NTU in Singapore. We have been working with them for a long time and compared the same thing, a gold tin solders bonded LED and our copper nanoparticle bonded LED, and you see the much higher intensity under the same power settings. And we also found that the electrical resistance is much lower, which you would expect for a pure copper system. So some bonding characteristics, we have done a lot of bonding, as you can see, from like 1x1, 2x2, 3x3, 5x5, and lots of other things, up to 15x15 on our CT adjusted substrate. This is a 6x5 on a thin lead frame that gave really very good results. Even after 850 thermal cycles, it still looks very good. Hot shear is almost the same after thermal cycling. So we get very good bond data for a wide variety of die. Here's another one, a 5x5 on, this is, the AMB silicon nitride, simply copper islands bonded with our copper material, and these die were gold coated, I believe. And in just about every case, we get bonding exceeding the 100 kilos. It just doesn't shear. That's kind of the limit of our equipment, what we can do. We can do this multiple times. Eventually the silicon will break.
And what is the typical curing or fusing time and temperature?
So as I said, we go to 235 peak temperature, and depending on the thermal behavior of the substrate, 4 to 6, at most 8 minutes. So very typical solder profile.
Thank you.
Yeah, and these we were able to run to pretty much 5,000 thermal shock cycles, and it holds up no problem. It works really, really well. This, by the way, is an SBIR. We're in phase 2 right now, and making very good progress here. So CT adjusted copper, I mentioned it already. This is Another implementation of the material, as I said, we can do plates of all kinds of things, heat spreaders, heat sinks. We can bond very large die. This is a very exciting implementation, which is we're able to fill, instead of trying to put copper coins, we can directly fill these large holes, any type of shape and size, with our material, and turn them into copper coins, basically. And then you can bond your die directly to it, and you can get the heat out on the other side and on the top. So you double your heat dissipating capacity. This is another really cool implementation where we were able to directly bond to a large L-SiC part, aluminum silicon carbide, heat sink or heat spreader plate, and put this AMB silicon nitride substrate basically bonded directly to it. So very cool stuff. Here's a little bit more information on the 10 by 10 that we put on this plate. We've done already several thousand thermal shock cycles on this, and it just doesn't budge. But when you put it on a normal bulk copper with a large CTE mismatch, you don't, in the best case, you get some strength, but often they just pop up when they come out of the oven because of the high thermomechanical stresses between the two. I don't think anybody else can do this. This is really great, and we just did it with a 15 by 15, and everybody wants to get bigger with the dies going 6 by 6, 10 by 10, and things like that. So this is a must. There's no other way you can solve this challenge.
And do you have to do anything special with the surface to treat it before applying your ink?
For these, we just put our another paste of our material down as a very thin layer, and then we bond it down. That way we get the maximum shear strength. That's all.
Yep.
Yeah. Here just we use CMC laboratories to measure our materials, and this is the one formulation with 3 ppm CTE at room temperature. Yeah. So this is my final slide. It's a wonderful material system. It is very, very versatile. It can do and solve a lot of different things. Here, just some things I showed. I mentioned the 15 by 15, the thermal vias. We're actually working with 2 of the largest PCB manufacturers. They're extremely interested, and we're in the process of actually transitioning that into to the big production equipment. I mentioned heat sinks, heat spreaders, lead frames, and much, much more. And these are some of the modules we're building right now. This is actually a high temperature one for that we're going to test to beyond 300 C and higher. So for the first time, you actually have a material that you can process at a low temperature, but you can take it basically to 900 C for operating conditions. And that closes my talk, and I'm happy to entertain any further questions you may have.
Thank you. Yeah, there are actually quite a few questions in the chat. I doubt we'll be able to get through all of them, but one that struck me personally as well as someone else is the material you're using to bond the die is obviously very conductive. And normal die attach is through either a TIM that's non-conductive or an epoxy that's non-conductive. Is there anything, I mean, do people have a challenge with the conductive die attach?
A challenge in what way? For processing or the conductivity?
Yeah, does the conductivity present any special challenges to the, I mean, to me, it's sort of like, okay, you attach to a copper sheet and the copper sheet is floating, so no big deal, but maybe there's something more there.
Yeah, I'm not aware of any issues. It works really well. You have to match the paste with the right fusion profile, so processing needs to be dialed in, like with most other die attach materials as well. But it's a great material. You can dispense it in many different ways, and it fuses very well. And then all the volatiles go away, and you're left with copper.
I think there's more questions around that. I mean, one
Sure.
post is, hey, could we put a dielectric material in there to really do the isolation? But let's not belabor it. What are the challenges associated with the material and the handling of it? Are there any you can point to?
We actually had to do a toxicology study on it for the EPA, and unfortunately had to do some animal testing, and it came out really, really safe. So you could eat it and you would feel unwell, but it wouldn't hurt you really or kill you in any way. So very, very safe material. The other safety feature, if you want, is we don't produce the powder. It's always a paste, and it's a very sticky paste, so it's not airborne. It sticks to just about everything, even Teflon, as we found out. So in that sense, very safe. The nanoparticles have a unique surfactant shell that protects it from oxidation. So we routinely, I mean, we always handle it in air. All the assembly, dispensing is done in air. There's no oxidation issues. So that's great. Maybe the biggest challenge is dialing in the paste and finding the right fusion profile with respect to a certain die size, because you have to worry about the diffusion path of your volatiles, that they can come out. So we've learned how to deal with that, and we're getting really good results now with very high shear strength, because we know how to adjust things. So you need a different formulation for like tiny surface bound components like an 04 or 6 or so on a circuit board versus a 5x5 die that covers the paste, and things have to diffuse out slowly. So these kind of things.
So one of the biggest challenges with multi-die integration today is the inability to rework products. I would also relate to that. I mean, does your product allow for reworking? Let's just put it that way.
Yes. It was actually a very early question or challenge when we started developing that for space systems where they have very, very expensive circuit boards. They can be like $500,000 because they're 24 layers and they have very expensive components on there. So you do rework those when there's an issue. And yes, there was a significant challenge, because you can't just remelt it at 200 C because it's bulk copper, right? So we figured out a way to use liquid metal embrittlement based around bismuth and similar materials, and cooked up a composition so that you can put this around your chip, for example, and it migrates along the grain boundaries really, really fast and pulls apart the copper. And then you can remove the chip, clean it up, and put a new one in place, for example.
Thank you. We're at the end of our time, but I got to ask a personal question.
Sure.
As a test guy, I always want a way to temporarily bond a chip to a thermal heatsink and then basically unsolder it or unattach it. Might your product be useful in that space?
That's an interesting question. It should be possible. It gets harder when the chip gets really big. 15 by 15, we haven't tried that yet. For smaller systems, or when you have like a QFN with lots of legs, that should be easy to do.
I like easy to do. Thank you.
I thank our sponsors, including Adventest, who's received the highest industry scores in terms of customer satisfaction survey from Test Insight, ranking as the #1 large supplier of chip making equipment. And I also want to thank Amcor and Cadence for sponsoring this event, and their sponsorship has enabled us to make these events free. So when you have an opportunity, please thank them for sponsoring MEPTech. And once again, I want to thank all of you for joining us, and I look forward to seeing everyone tomorrow. Thank you.